Okay, thanks for coming. This is the derived algebraic geometry. So the class meets Tuesdays and Thursdays, 3 to 4:30, right? 4:30 p.m. Okay. So as many of you know already, this class has a web page in the CMSA, in the Harvard CMSA. There's a web page. I have put at least the materials that I'm looking at while preparing for the course. So the material is all there, syllabus is there. I'm kind of looking at all different sources, kind of summarize them here. So I'm not following a particular one or the other. But mainly this is based on the constructions of Cohen and Vetsozi. So Cohen and Vetsozi, oh, how do you write Vetsozi? Two Z's. Vetsozi, two Z's. S?
No, two Z's and one S.
Ah.
Oh, would be one.
Cohen and Vetsozi. One of the we have written several papers. The ones I'm looking at, I mean, you can search Google any of these things, so you can look at this Simplicial paper that any of these two guys have written on Simplicial, pre-sheaves, and derived algebraic geometry. Derived algebraic geometry. At least the beginning of the class is based on these papers, multiple drafts that we have published on this topic. Okay, just to tell you what is the goal, we just talk about things that majority of you already know. Kind of, we start from very simple things, model categories, the naive definition of the stacks over categories, one stacks, two stacks, n stacks. Then we will go to stacks of objects valued in simplicial rings, and so on. Then we discuss about the notion of, categorical notion of the schemes. Then we restrict to, simplicial commutative algebras. Then we discuss about the schemes which are defined over these simplicial commutative algebras. Then we will discuss about kind of differential structure of these things. So, drive the schemes that are cotangent complexes, tangent complexes, things like that. And always we have in mind to find applications of these constructions in moduli theories. At least for me, because I am just a regular algebraic geometer, not a derived algebraic geometer. For me, I have somehow encountered examples where using regular algebraic geometry, you cannot calculate sometimes invariance over certain moduli spaces. So, for instance, moduli spaces of coherent sheaves on fourfolds, for instance, are one example of these things. In particular, they must be Cauchy on fourfolds. Then we discuss about applications of derived geometry in these things. So, derived geometry allows you to obtain a machinery that you can do some kind of intersection theory, which is different than intersection theory in normal algebra. So we discuss about those things. Hopefully, we discuss about this machinery of PTBV, contact, shifted symplectic structures. Which moduli spaces have shifted symplectic structures? What is the implication of having these structures over moduli spaces? How can we use them to define even invariance in cases where we cannot define invariance on regular applications? So this is where the course is kind of going. Okay, so, and one thing I should say, that's Dennis over there, sitting, Dennis Borisov, raise your hand. Dennis is a researcher here, and he's doing his research here as my postdoc, and he's in fact more expert in these things than me. So Dennis will probably, I need his help, so because he knows things that he's expert in, and he can lecture those things, but actually I was thinking maybe you guys also can participate. This is a good way of doing this, especially some of the students of Dennis, right? So maybe we should do this. So at the end of this class, if you are willing to participate, unless I click on you, which I already clicked on, at least one person in this room, maybe you should take somehow some of these lectures and lecture. That would be Okay, so let us start. So this is the definition of a derived scheme. Derived scheme. Let's just give you a definition. Definition. Derived scheme. Consists of a pair x and OX, right, like every scheme, where X is a topological space. And OX is a sheaf of commutative simplicial rings. Simplicial rings on X. Okay? On X. Such that the following conditions are satisfied. Okay, so this is essentially something that we will be discussing in the following 3 sessions. So 1, to ring the space, x and pi 0 whole x is a scheme. So let me just write down these conditions and then I will explain. 2, for all I bigger than zeros, the homotopy sheaf I of the structure ring of this scheme is a quasi-coherent sheaf of modules on the scheme x and pi 0 whole x. Okay, so this right now you should think of as a black box. If you understand it, that's fantastic. The following 1 or 2 sessions will be absolute trivial for you. If you don't understand it, the following 2 or 3 sessions are basically trying to a little bit elaborate on these sentences I put in.
In particular, we're going to define a sheaf.
Yes, exactly. So this is the definition. This is somehow I'm telling you the end of the story for the following 2 sessions. This is where we are going. We would like to make sure that we understand every word in these sentences. Okay, but just looking at words at least, homotopy sheaf is, so it seems like the derived scheme is some kind of naively homotopical perturbation of a naive scheme. And we hope that this could be playing the role of the naive scheme for us. Okay, but I need to define things so that we can understand what these mean. Okay, so let's just really go all the way down and start from the scratch. So let's talk a little bit about model categories, the review of model categories. Model category of simplicial pre-sheaves. Okay, so let this pair of C and tau be a Rothenbeek set. That is to say, we are given a category which is C for us, together with tau, which is our growth topology. Okay? Together with growth and leak topology. So let me ask you something here. Is there anyone here who doesn't know model categories of growth and leak topology? Okay. good. Because I asked, and for instance, there was a suggestion that I could have come and told you, convince yourself that you understand these things. But some people actually told me, we would like to see some kind of a brief review. So, okay. So let's start from the category and the growth in the topology. So growth in the topology is the following data. So what does it mean? For any object of this category C, we have a family of covering of this object of sheaves over X. These are subfunctors of the representable functor. Let's call it h of x, which is defined as homomorphism blank x. This is what the seeds are. Okay? Which satisfy the following conditions. So one, for any object of this category, h of x itself is an element of this family of coverings. Two, for any morphism, f of y to x, there is this notion of pullback of the functors that you can pull back of elements in the seeds. So, and any u in the family of sheaves, we have a notion of pullback, which is defined by this product, an element of family of coverings of y. Okay. Now think about the category of topological spaces and convince yourself that open sets actually do satisfy those properties. You can cover some topological space by open sets, and those are morphisms, and they do satisfy this property. So, almost everywhere, if you didn't understand the statement, you can literally specialize the category of topological spaces. Okay. So, and three, that X be an object of this category, U be an element of this covering of X, and V be any sieve on X. Okay. If for all Y in this category, and any F, remember that this is the family of subfunctors of the morphism, these are morphisms to Y. So for any Y in this category, and any F, which is an element of the set of homomorphisms from Y to X, we have F star of V in the covering of Y, then V itself should be C over X. Okay, so this is what it means that for a category of objects defining some notion of topology. In some sense, this gives you a way of covering objects in a category. Objects that behave like open sets. Yes. Okay. Okay. So this is growth in topology. Now let's define the following. Now, this is called the site. The category with this topology is called the site. It's called the Grothendieck site. Now, given a Grothendieck site, we would like to define a sheaf of it. We have its associated category of pre-sheaves. Category of pre-sheaves, which I showed this way, which is the category of functors. The category of functors from the opposite category. That means that, of course, we know it. Objects are the same, morphisms are reversed. Opposite category, opposite of the category C2 sets. Okay, so this defines for you a pre-sheaf. And now what's a sheaf? It satisfies further conditions, so you can imagine that it should be associated with this subcategory of this thing. So the full subcategory of pre-sheaves is called the F, so we see opposite sets, and such that for any object of the category C, any covering of it, or any U in that covering, the natural morphism f of x is come from x of x to f to come from u to f over this category of pre-sheaves is an isomorphism. It's the bijective is just bijective. What's a sheaf? It's a pre-sheaf that glues over the intersections of patches. And convince yourself that this is somewhat similar to that statement. How do you convince yourself, restrict yourself, specialize to the category of topological spaces? Think of C being open sets. By the way, any comments? Let me know.
Sorry, one question.
Yeah.
About your notion of category.
Mm-hmm.
What are you using?
Huh?
Are you using infinity one category yet?
Not yet. Not yet. Not yet. We will get there. Let this SPRC be the category of simplicial objects. Objects in the category of pre-sheaves that I define this way over this category C.
So is this what is this part?
So first, we are looking at some category of pre-sheaves on a given category. This parting making sure that this is a sheaf.
I reckon a sheaf condition.
Yes.
So
This is the pre-sheaf condition that gives it category of pre-sheaves on a category. Now on this category of pre-sheaves, I am constructing some category of simplicial objects, which I call simplicial pre-sheaves.
I'm confused. Isn't a pre-sheaf just a pre-sheaf sets just a functor from C up to sets?
And I need to just tell you what does it do to the elements of covering of some object of the category. And that is what's the definition is.
This is a remark, not a
Yes,
quotation.
it's just a remark, yes.
And when you say like a simplicial objects in this category, it's different from the
Absolutely.
it's different from the functor, the sheaves. The functors from C up to simplicial
Yes.
sets.
Yes.
They're not the same.
No. The category of simplicial objects over these pre-sheaves is the one that point-wise, fiber-wise, over every object of the category gives me a simplicial complex made by object of that category. Does that make sense?
Yes, but I thought you were going to consider the pre-sheaves of simplicial objects instead of simplicial objects of pre-sheaves. Which one do you actually want? Are you sure you really want
I would like, yes,
the simplicial objects
Simplicial-
of pre-sheaves?
simplicial objects of these pre-sheaves. What? Is that right?
They're the same.
They are the same?
It's the adjunction of factors and product of categories. So simplicial objects are maps out of simplicial diagrams into the category, and then pre-sheaves are maps into that category. So it's you either map out of the category times delta into the sets,
Okay.
or map out of the category into form.
In
from that.
particular, the categories have to be small for those two features.
Well, we can ignore the size issues by just choosing universes.
Yeah. So via some argument. I should also say, these are a little bit category theory. But goal actually really is to later do more geometry and algebraic geometry. So later when we go to commutative simplicial rings and so on, it becomes really very much similar to the flavor of Grothendieck or EGA or Hartshorne. So that's where it starts really becoming more geometric. Nevertheless, this is just a review. If you have comments, yeah, please let me know. Okay. Now, definition. Definition 2. Let F to F prime be a morphism. In this category of pre-sheaves on a given category C. Now, 1, the morphism F is a global vibration if for any object of the category, the induced morphism f of x going to f prime of x is a vibration. Okay? Vibration of what? Vibration of simplicial sets. Okay? So objects go to objects and morphisms go to morphisms. For the maybe I should have put this comment. Okay. So this statement is actually, this definition is trying to say you want to understand morphisms between objects of this category of pre-sheaves valued in simplicial sets. Everything is understood fiber-wise. If it holds true for all objects of the category, then
Wait, sorry, I'm confused. I thought your PR of C are pre-sheaves. In particular, they're valued in sets instead of simplicial sets.
yes. So
I think he upgraded.
yeah, I upgraded it. Now, via this discussion, we can also upgrade it. So simplicial category of simplicial objects over the category of pre-sheaves is the same as the pre-sheaf of simplicial sets.
But your notation is still, I thought, what is PRC?
PRC is the pre-sheaves on
what? On C?
the category set.
Valued in
Simplicial sets right now. We have upgraded it.
simplicial sets.
Yes.
And when you say vibration of simplicial sets, you have chosen a model structure of
That's right.
simplicial sets.
Yes.
What
Maybe
is-
this is the comment I wanted to actually say. So this is, we have picked that model structure. So for the model structure for the model, the standard model category structure. Is this called confibration or something like that?
Yeah, I think that's what it's called.
Confibration.
Can you explain? Sorry. Because first, if it's a billion groups, then I know how to get a model structure. But if it's simplicial sets, how do you get a simplified model structure? This is
So there are, you need to specify two classes of maps. You can say what are read equivalences,
Yeah.
which the easiest way to say that every simplicial set can be realized as a topological space. You compute the homotopy groups, and then the map is with equivalence if it induces isomorphism of homotopy groups.
And the fibration and cofibration are defined in the same way?
No. So the fibrations, there's this very important concept of confibration, which is essentially lifting of a path, or a very quick way, but not really interesting, is to do cofibration, which is using some generating maps, the acyclic cofibrations and so on. But essentially, the most important thing that you have to remember in this entire story is the notion of confibration. That's the most important thing, and that is lifting of a path or lifting of a simplex. If you know that a horn in a simplex lifts, then the entire simplex has to lift. And that's this property is a lifting property, and if a map of simplicial set satisfies this has this property, then it's a fibration.
In particular, if I replace sets by abelian groups, do they agree with the model structure you get from the chain
Yes.
complexes?
Yes. So for abelian groups, for simplicial abelian groups, it will be much easier. So fibration will be just subjective maps, component-wise, and
The other ones consist of projective objects.
excuse me.
The other ones consist of projective objects. In cofibration.
Yes, exactly. Yeah. So the simplicial groups, everything is much easier, but in fact they inherit the model structure out of simplicial sets. Thank you.
So, the morphism F is a global equivalence. If for any object, again, in this category, the induced morphism F prime of X is an equivalence of simplicial sets.
Oh, you mean bank equivalence?
Yeah. Global equivalence. Maybe this is also, I add this, the morphism, these are just, almost, so the morphism F is called global cofibration. A global cofibration. If it has the right, this is something basically that is what you're saying. If it has the right lifting properties.
You also don't need to define it, right? Because you already defined what is fibration, what is weak equivalence. So
Why don't I need it?
Because global collaborations are just the ones which has. It's what you're saying. It's precisely what it's defined.
oh, okay, I didn't see the okay. Sorry.
With respect to every vibration, which is also an equivalence, right? So it's also an equivalence. Okay. So now you define this category of pre-sheaves, taking values in simplicial sets, and then you can define also these homotopy rules for it. So let us now define the sheaf of the homotopy. The homotopy sheaf of a simplicial pre-sheaf. This is something that define a pre-sheaf this way. So pi 0 in this category of simplicial pre-sheaf is taking you from opposite C category to, again, the sets. And for any object in the category, it sends it to pi 0 of f of that object. And everything is defined by this.
Sorry, I'm lacking background in simplicial sets. Could you define pi 0 again for simplicial sets?
You know,
Take associated
take
associated complex and then take pi
complex
0.
and then pi 0.
Is there more categorical way to define this?
Not to my knowledge, I don't think.
Because like if you instead of sets you have like a Abelian category, then this can be defined as the homology of the associated cochain or chain complexes.
Well,
There is.
I think in particular case of pi 0, you probably can compute it also linearizing, but this is much simpler. So simplicial sets have a sequence of sets, right? Dimension 0, dimension 1, and so on. Each element in dimension 1 has two maps to dimension 0, the source and the target. That gives you a relation on the set which is in dimension 0. You complete it to an equivalence relation, and then pi 0 is the set of equivalence classes.
Good that Dennis is here, so we can see this. Okay. So, similarly, actually, the other Dennis suggested that maybe we shouldn't cover this. So, at least some of you guys have seen these things before. So he said maybe we should pass this, but this is just for the sake of completeness. All right. So similarly, for any x in this category and any zero simplex, let's call the zero simplex f of x. So these are taking values in simplicial sets, and then we define pre-sheaf RPI sending the simplicial set of values. Well, let's define it this way. It sends, so objects in here are realized by morphisms from objects of the category to that one that you fixed. So let's call these things f. So these things will be sent to pi I, the homotopy group of f of y around centered at pullback rows. This is how you define higher objects, higher homotopy groups. Okay. And this is the pullback of the zero simplex from y to
you explain this notation?
The notation is that you pick some zero simplex for the object x, and then you put it back. Now, this category realizes all objects of morphisms from all objects of category to a given one. You have the zero simplex that you obtain by looking at the fiber of this functor over that object. You put it back. Then you can, in principle, you can just define, homotopy group of f of y, the simplicial set, centered at that point.
Because I just also know this is I for
How
any,
do
for any,
you
for any simplicial-
calculate
yeah, for any
homotopy?
simplicial object fy
Yes.
and some zero simplex in f of x.
Yes. Instead of this, though, I pull back. I look at the pre-image of the zero complex in y, but I'm still trying to define higher homotopy group of f for a given object x. Right?
And yeah, no, I don't understand. Maybe it's simple.
So you should think about always switching from simplicial sets to topological spaces. Now, a map from Y to X, because F, the capital F, is contravariant, corresponds to a map in the opposite direction for topological spaces. Choosing S, means to choose a point in that topological space.
That's right.
And now, how do you compute a homotopy group centered at the point? Well, that's algebraic topology.
Yeah. Exactly similar to algebraic. You're looking at higher homotopy groups centered at that point.
I have a question.
Yeah.
So you're defining it with respect to any base point?
Yes. I don't think that there is any problem. Yes. The zero set, as long as it's zero set. Yeah, that's right. Any base point. For a choice of a base point.
Oh, you're on the simplicial set. Yeah, of course.
Yeah, there's
Of course. Yeah, of course. Yeah.
Okay. So then there are some statements about these homotopy groups as well. Here, by the way, just for completeness, this thing, and which is the zero simplex on f of y, is the inverse image. Inverse image of base points and I f of y f star of s is the homotopy groups are the homotopy groups of simplicial set. Simplicial set f of y based at that point.
So probably you want to put s into your notation of the functor. Does that depend on choice of s?
That they don't put s in the function.
It does depend, of course, but
Of course.
just like computing the homotopy group topological space,
Yeah.
depends on which point
Always
you choose.
fix a base point anyway.
Why you should put
Okay. So continue. Let's see, maybe I should say how should if you have a morphism of simplicial pre-sheaves, how do these homotopy groups associated with them communicate with each other? So this is the third definition. If you have a morphism of simplicial pre-sheaves, then one. Morphism F is a local, again, I mean, this is similar to the previous definition, is a local equivalence if it satisfies the following conditions. One is that the induced morphism pi 0 of f to pi 0 of f prime should be an isomorphism of sheaves. These are homotopy sheaves, so should be an isom of sheaves. This is one. Second is that P for any object in the category and any choice of a base point and any integer, the induced morphism I f centered at S to I of f prime centered at pullback of S is an isomorphism on the, of course, on the
You want to pull back to the first thing, right? You want to pull back to the first thing.
pullback what?
You want your pull. You want it to be the pullback to the base point of f.
That's did I make a mistake? No, that's fine. Pullback of base point of f, that's right. This is a morphism of sheaves on here. So I'm looking at objects in here which are given by things like this. And then over here, I look at the fiber of f on this.
Oh, okay.
This is the big one.
When you write sheaves, you mean pre-sheaves.
Pre-sheaves. Okay. Again, there's this notion of co-fibration for the morphisms as well. So we would like the morphism now I understand what you're saying. Okay. Yeah, so this, now I understood what you're saying. This F is this F, not this F. So that's what you were saying, right? Yeah. The morphism F is a local cofibration if it is a global cofibration in the sense of previous definition. It's a local cofibration It's a local cofibration if it has the lifting property every local cofibration, which is a local equivalence. But let me summarize what I'm trying to say in here by the following remark. Because at least I am an algebraic geometer, not a derived algebra. What is this trying to say is the following, all of this definition. Remark is the following. This definition endows the simplicial pre-sheaves on a given category C with a model category structure. And we say that it has the local modulus structure. Okay.
So you say what you're trying to define right now is the same as what you were defining?
Yeah.
earlier? So earlier you had a
Doesn't mean all of the nice cofibration properties and the lifting properties.
This is just the pullback of the model structure
From the
superficial
base,
sense.
that's right, in some sense.
Why
To
are
me,
you giving- why are you giving two
Because-
definitions of homotopy equivalence or big homotopy equivalence and not saying?
it's the same.
It's the same. I'm not giving any different definition. I just a remark that this is the modulus structure on the simplicial pre-sheaves.
Even on the nose, they're the same.
Oh, but the second, do you mean local cofibration is the same as global cofibration?
That's right. Thank you. This one.
Yeah.
That's correct. That's correct. Yes. Okay. So, okay. So let us, let's see. Yeah, let's define some, we need some further definitions. Okay. So, remark, maybe, let's see the remark. Remind yourself that what is called the hypercover, covering of an object of an object X in the category C is the data of simplicial pre-sheaf F together with the morphism from, this is the hypercover of X, and satisfying the following two conditions. One, that for any integer n, there is a pre-sheaf, the pre-sheaf H of n is a disjoint union of representable pre-sheaves. And 2 will all n bigger than 0, the morphism of pre-sheaves of sets. Pre-sheaves of sets. I mean, these HNs are, okay, so let me write it in here. These HNs are isomorphic to homomorphisms from the canonical n simplex to your hyperpower. And there is a morphism from these to boundary of these n simplices times yeah. So you can of course convince yourself that this will be the algebra of these things will be these guys will be in some sense objects over the algebra of these guys. And so you will get this natural map. H is the hypercover which has a morphism to the X.
Oh, sorry, is H an object of C?
No,
Pre-sheaf.
it's a pre-sheaf.
So what do you mean by the morphism from H to X?
His x is hx.
That's right. Yeah.
We should probably write hx instead then.
Yeah.
No, that's h. The other one
Right.
is hx.
Let me see.
Just saying that the X, you're using X, you could just embed into the pre-sheaves category.
Yes, that's right.
To make life. It's
I think as written.
It's okay if it's
No, as
okay
written
to
is
write
very
it.
confusing.
I
because-
think it's okay to write it H.
No, because what is x? X is an object in C.
And the C. That's right.
Yeah, but you're really viewing this as a morphism in category of simplicial pre-sheaves.
Pre-sheaves. That's right.
Therefore, your x should be h of x, which is a constant simplicial pre-sheaf.
So every object of the category, of course, has an embedding into the category of simplicial pre-sheaf.
Oh, yeah, for beginners, very
So the
confusing.
yeah.
So what's the meaning of F?
F is just the H.
H. So this is the problem. Okay, now.
Yeah, but I still think you should write h of x on the right-hand side of the arrow. For the right-hand side of your arrow.
Mhm.
Otherwise, it's kind of confusing.
Yeah, that's right. I agree. Okay. Okay, so I think this condition, the second condition that I wrote in here, can also be restated in the following way. The second condition, condition 2, is nothing but can be restated as for any object in the category, you have this commutative diagram kind of. This guy just put the com y to x, and this is h of y that gets mapped to there. A sequence square diagram of simplicial sets. There exists a map, basically a covering C U in the covering of Y, such that for any U to Y, for any map in the CU, for any big U in little u, there exists a morphism delta n to h of big U, making the following square commutative, making the following commutative.
Sorry, before you raise the second
Yeah.
part, I don't understand the condition. The condition says the morphism of pre-sheaves. Said what?
But there is a morphism of pre-sheaves this way.
There is. There
There is
exists.
a morphism.
For any n, there exists a
Yes.
morphism.
So before I delete this, let me just put it.
Was that part of your data?
Yes,
Of H?
that's right. So it means that whenever you have a commutative diagram like this, there exists a morphism this way. Yes. I spelled out basically these two lines here. So, sorry. Y to X. There is some morphism.
No, sorry. I don't understand. Because is part 2 not automatic in your definition of hypercover being a morphism pre-sheaf? This can't be equipped with a morphism pre-sheaf?
It's not automatic, it's part of the definition of the hypercover. I don't see why it is
You want
automatic.
to say it's an ISO?
No, I'm just saying there is a morphism. This is statement.
I mean, automatically you have you automatically have a
Yeah, you
morphism.
automatically
and-
have a morphism.
and
Because from every simple delta n to h, you can automatically map to both sides, and they agree. Wait.
No.
They don't automatically agree on the.
No.
They don't automatically agree.
You need to fill a hole, and the question is, can you fill this hole? And,
If it does, then.
That's the condition of covering. The hypercovering means that you can do it locally.
Yeah. I mean, this is generalization of just like basically complex. It's just like what is it? In some sense, simply connected space, right? Covering things, right?
Yeah, it's a generalization of a check cover.
Yeah,
That's
that's
a
what.
check cover, then.
Oh, that's a good comment. Actually. Yeah, maybe I should write that. Let's just put it. Yeah. So remark. This is a generalization of Chipner. Yeah. What should be is the Simplicial resolution. Resolution of an object obtained by repeatedly applying the covering families.
Can I ask again? So this the condition 2 means if you consider the if you consider the n level hypercover Hn, take the boundary of this hypercover, and then you project it down to the base. You should obtain the boundary of Xn. Is that what this is saying?
No, but not every time that you have boundary of delta n, it comes from delta n, right?
Not. Say that again. Sorry.
If you have a map out of the boundary of big delta n,
Yeah.
A priori you don't know that it comes from a delta n, because there might be no simplex whose boundary is this. There is a hole. And in the usual check cover, if you have 3 open subsets,
That's right.
you think about them as boundary of the two syntax.
I see, I see.
Yeah, and then the intersection of them would be the thing that fulfills the whole. The question is, can you find an open subset, or a chart in this case, that actually fills this hole? The condition usually is that this you can, that's the check cover. In the more general situation is that you have to chop it in smaller pieces to be able to fill it.
I'm even confused why, like, okay, so I understand I understand this definition. I'm not seeing why this is the same thing as what you wrote. The existence of that morphism. The existence of
I'm covering it basically. For every object of the category, I take elements of some sheaf. And this statement is basically fiber-wise. This statement
okay.
here is the
Yeah.
fiber of that
Understood.
statement
Yeah.
over every object of that. So, so let's see. I would like to have still some time. This property it is called lifting property. Lifting property, and it is a local analog of the lifting property characterizing somehow trivial vibrations of simplicial sets. So there are some further properties, but I think you can just find those in the literature. Now we can prove that an object of pre-sheaf F in the so if and only if the following conditions are satisfied. Following conditions are satisfied. For every x element of this category is a special set f of x is fiber. Two, wherever x in this category and any hypercovering, again h to x, and the natural morphism what?
Is fiber and complex.
Yes. But this is the notion of fiber, and for this category anyway, this is the definition. The natural morphism f of x to homotopy limit So this one is a little bit. F of H of n. These are from delta to x is an equivalence of simplicial sets. So something I should say here, these two conditions, these two conditions are analog of sheaf conditions, in fact. Sheaf conditions. In the sense that this F is some, in the sense that F is a pre-sheaf of sets, considered as simplicial pre-sheaf. Somehow constant in the simplicial direction, but I don't want to put that.
So for two,
in here.
do we really need to choose a hypercover? Like, if I just choose all covered, right? This be okay?
If you choose what covering?
All covered.
Well, no, it is not. As long as they do satisfy the condition of hypercover, you can refine your cover, yes, then that's fine. But all covers, I don't think. Right? I mean, think about sheaf condition for a pre-sheaf. Just the categorical version of that. So it doesn't glue. Right? Am I right?
I didn't understand this question.
It says if you pick all coverings instead of hypercover, then it doesn't work, right?
All coverings?
No,
Well,
of course not.
Yeah, if it is a hypercover,
Then it works.
well,
But it has the gluing, right
any
gluing
cover is
condition.
also hypercover, but in particular, but yeah. Anyway, it has to be for all hypercovers, not just for covers.
For all hypercovers, yes, that's good. Of course. Did I understand?
So do you mean a sheaf is a fibrant object?
In the category of, yeah, that's right. This is the condition that the sheaf will be a fibrant object in the category of simplicial pre-sheaves. In some sense, the pre-sheaf will be a sheaf if it's a fibrant object in that category. In terms of hypercovers. Now again, I ask you to, just to understand this thing, restrict to the category of topological spaces and ask your sheaves to be sheaves with values in groups or rings. You have embedding of the groups inside simplicial groups. And just recover the definition of sheaf from Hartshorne. Except now we are picking these open objects of, the open sets are being basically objects of the hypercover, elements of the hypercover. This is what we are doing. It's just a categorical version of the definition of the sheaf. Sheaf taking values in simplicial sets. Okay, so here's so maybe this is useful. So definition. This is the most formal definition of a stack. An object F in the category of simplicial pre-sheaves over category is called a stack if for any element in the category and hypercovering H to X, the natural morphism f of x, again to the homotopy limit in the category of simplices, f of Hn is an equivalence of simplicial sets. Wait, so an object we call stacks. If this is the first condition. Second condition is that the homotopy groups these will be called the homotopy category of the set. Called the homotopy category. On a side. Yes, go ahead.
This is not the second part of the definition, right?
No.
And you have a 2 there. I don't think this is 1, 2.
Yeah. Okay. So now think about definition of the stacks with group width sections that we have in usual algebraic geometry. And try to match this with that. As a special design. I would like to give you some examples of the stacks that you have seen before. There is this.
Sorry, could you rewrite what you
Yeah. This is, I mean, the homotopy groups. Are called homotopy category. Category of sets. On the site, on a given site, or the category of the stack space.
Is that the homotopy category or homotopy group?
I think you mean homotopy category, right?
Yeah. The homotopy.
And do you really mean the homotopy category of entire
Of the entire category of simplicial
pre-sheaves?
Yes.
Simplicial pre-sheaves.
That's right.
It's called homotopy category stacks.
Yeah,
Why is that? Why do you call that?
it's just a definition.
I mean,
The name. It's
you
just-
give a definition of what a stack is.
yeah.
You're saying
It's trying to say in this category, the notion of the stacks are putting equivalent to each other with the word homotopy, up to homotopy.
don't you?
Think about how you go from category of sheaves
Yes.
to the derived category.
Yes.
Now, objects of the derived category can be as stacks, right?
Yes, but what I'm saying is that right now, if you just start with category of pre-sheaves, and just take the homotopy category, you're just directly calling that the homotopy category of stacks, or
Yes,
or do
we
you
were
mean,
calling that.
or do you mean the objects, or do you just, sorry, how should I say it? Like,
Stacks are fibrant objects.
yeah, should
The
we?
stacks are fibrant objects.
Yeah, but they have same homotopy category, so they.
Oh, yeah, okay, understood. Yeah.
It's exactly similar to going from
Yeah, yeah.
sheaves to objects in the derived category. Right? Objects in the derived category are fibrant objects, and their equivalence is up to homotopy. Okay. So some examples of the stacks. Let's just do it. One of the major examples of the stack is the algebraic stacks. Maybe this is a good place to finish this today. Algebraic, some examples. So I would like to, my preference is that to get as close as possible to algebraic geometry and get away from topology. But let's do algebraic stacks a little bit. Can you consider this is my notation, commutative, the category of commutative rings to be a map from, to be the opposite category. Okay. So for an object in this ring, we denote by the spec of A. This is exactly what we have seen before. The spec of A, the corresponding object in let's give this tilde in this category alpha. Right. So how do we construct the algebraic stack? We endow this category with an Etale topology. With Etale topology. What is Etale topology? Let me remind you. So now this is a category. We are defining a growth index site on it. This is a good example, right? So what are the open covers of objects in this category? Remark. So this is a remark. Maybe a morphism of rings in this category, in the commutative category. Let's call them A to B is Etale if it satisfies the following. One, that B is a flat module, is flat as an A module. Two, that B is finitely generated. Finitely generated as a commutative A algebra. As a commutative A algebra. Well, that means that locally B kind of looks like some ring structure like this. The quotient of a ring, an element.
Isn't that finally presented?
Finally presented or finitely generated as an A algebra. That's right. Yes, that's right. its corresponding affine is in the finite difference. So this is so you have Etale morphism on rings, and so but there is a third condition, which is B is flat as a B tensor B over A module. This is equivalent to saying, if you look at Hartshorne, this is equivalent to saying that the relative sheaf of differentials of B over A is 0. And you can think of this many ways, where omega 1 BA is the B module of relative Kähler differentials, relative Kähler differentials. That is, this is a just review of algebraic. This is the object that corresponds to the functor sending a B module, sending a B module to the B module M to the set of A linear differentials, A linear derivatives. B with coefficients in N. I mean, I'm just spelling out, it's not a bad review, it's just a review of Arch. So, I mean, if you look at the level of the spectrum of these rings, the Etale morphisms are smooth morphisms of relative dimension 0. You can do that too. Okay. So what is the property of Etale morphisms? So Etale morphisms are stable under phase change. And composition in the category in this category of affines. Right? Okay. All right. Now these are the ones which are going to give us the covers and the hypercovers and so on and so forth. A family of morphisms A to AI, right, is an Etale covering. Etale covering if each morphism A to AI is Etale. AI is Etale. Okay. And then there is, I'm putting this comment in here. Well, and if the family of base changes, base change covers, base change functors, which is, this is a base change, right? It takes you from category of A modules to category of AI modules. Is conserved. It's conservative. It's the same statement as the flatness of the ring B, but for every element of this cover. Okay? So it needs to be, it's basically saying that for a given family, for a given cover, you need to stably base change over members of the cover, elements of the cover. This defines a topology. Topology that a sieve on a speckle A is a covering sieve. It's a covering sieve if it is generated by an enclosed covering. Covering sieve if it is generated by an Etale covering family. Okay. So now that you have this category of commutative rings, and the opposite category, you have the right notion of growth index height on it, then you can construct the stacks exactly as before. This time there will be algebraic stacks. So very quickly, schemes and algebraic n stacks. So the schemes and algebraic n stacks. I'm just following the same steps, formal steps. So for some speck of A, an object of this category, consider the pre-sheaf represented by the speck of A and E. This sheaf, if I can call it like this, it's a morphism from this opposite affine category, which is the same as the category of commutative rings, to sets. Remind yourself that the schemes are given by sheaves ring valued sheaves. So think about that. Okay. By setting what happens if I act by this on some B, then it will be homomorphism from A to B. This is exactly compatible with usual notion from the scheme. It can be seen. This is the faithfully flat descent. Faithfully flat descent. That this pre-sheaf, it would be a sheaf. This pre-sheaf would always define a sheaf.
In the Etale topology.
Hmm?
In the Etale topology.
Yes, yes. Exactly. On the Etale, yeah, that's right. On the Etale topology, that's right. And this defines, and this defines a faithfully flat functor applying to homotopy category of simplicial pre-sheaves simplicial pre-sheaves on this category affine. Any object in this homotopy category, any object in this homotopy category of the simplicial pre-sheaf set on this of the form step of A will be called an affine scheme. Called an affine scheme. Okay. The full subcategory of this homotopy category consisting of all affine schemes do you know what it is? Is the full subcategory of this homotopy pair category consisting of all affine schemes.
Derived.
No. It is just right. Good. Any object, I mean, this is much bigger category. This is much bigger category than this category. We are constructing this homotopy category out of simplicial pre-sheaves over this category. And think about those fibrant objects. Now the ones whose resolution is just similar, I mean, are just honestly given by this are affine schemes for us. And there is a full subcategory of this category inside that ginormous category that has all of the objects of this form. And of course, that's nothing but the original one. Okay. So this is the scheme. So you can actually see that the affine schemes can be defined exactly following this formal notion of formal notion of something as some kind of using some object given by simplicial pre-sheaves or category. Just do an example of these quotient stacks, for instance, and then I think I would like to move us, somehow quickly to the simplicial commutative range and notion of derived stacks. The idea is always the same. You construct the derived affine schemes and then you cover them and you use them to construct bigger derived schemes. So on. Yeah, I think this first session is the most categorical session that we had. The rest of it would be more dimensional. Okay, thanks. Anyone would like to, I think actually it makes sense for this class, because these are kind of really recent constructions and so on, especially when we go along. It makes sense that you guys also take part. So do you want to do it one by one? It's much more fun this way, believe me. No comments? Do you like to do it? Do you like to do?
Maybe later during the semester.
Later?
Yeah.
Okay. At least Dennis has agreed already that you should do it though.
I mean, I will.
This is your
sure. Like I would like to do a later talk.
butter.
No, I just would
bread.
like to. I would like to do a later talk.
You should. This is your butter and bread.
I mean, like if I'm doing this, like if I'm constructing an affine scheme, I'm not really learning anything. So, like,
Okay.
What is that thing?
This is the controller for the